We carry on with the zero-to-quake-3 project today. The idea here is to start with absolutely nothing and see if we can get an implementation of, I guess, as much as Quake 3 as we possibly can, using a combination of Haskell and Vulkan. So just recounting what we have done. Big milestone from the last stream, the long stream, but we finally have a triangle that we can render, which sounds like we're miles and miles away from anything interesting, but we're actually not. We're getting into some interesting stuff now, and we also spent a bunch of time at the start of the stream doing some refactoring. So we now have a nice DSL for building Vulkan structs. So we actually just used the one that came with the Vulkan API library. So it's this kind of thing. And we also dealt with a bit of resource cleanup, which was I've tagged as correctness. There's one more bit of kind of correctness that I want to have a look at first, which is just correctly using this Vulkan loader library, because right now, like you'll see, it's working fine here, but if I exit my development shell and re-enter it, it's not going to work because it can't find libvulkan, and the only way to get around that is by currently exporting Vulkan loader onto my LD library path, which is not correct at all. And I think this is actually going to be quite straightforward. I think all we need to really do is add a library dependency onto Vulkan loader, or maybe it's just Vulkan, because it's looking for libvulkan. So let's do extra libraries Vulkan. I think that's really all we need to do here. No. That shell is unhappy, this one's happy. Strange. What if we go back in? So, my hunch was correct. We do just need to put it in extra libraries. But the moment I do that, GHCID falls apart, which is a little bit of a shame. Oh, cool. Glad to hear some other people are having a play around with Vulkan. Let me know if you get anything interesting. Let me just have to Google for like GHCID extra libraries. Nothing too useful coming up there. What is going on? It's so strange. What if I just load this in GHCI? Source. It's happy in here as well. So what is GHCID doing that's so different from just normal GHCI? Oh, it's Cabal REPL that messes up. So what about new REPL? Yeah, so will I be consulting Quake 3 source? I am almost 100% certain we will look at the Quake 3 source at some points. So for people who are unaware, just as a bit of background, I have done a similar project to this before, which is the HS Quake 3 project. So this was a Quake 3 map viewer written in Haskell using OpenGL. Let's wait for this to load on what seems to be my 56K modem. So it's pretty. I think it's pretty close to how Quake 3 would have rendered maps. That used OpenGL and interpreted Quake 3 shaders. But we'll probably have to. I kind of want to do that from scratch again. I don't want to rely on this code, so we'll probably pull up the Quake 3 source code just to work out how that works. Dynamic library modeling. It's like a panic. if I could just use normal GHCI, I'd be happy. But then that says no files loaded. GHCI source. Oops. That works. Maybe that's going to be good enough. Is it like... Okay, we'll stick with that. So I don't know why Cabal Raffle doesn't work, but this gets us back to compilation. So find out how to correctly use Vulkan Loader. I'm going to call that done. Okay, let's carry on with some features today. So move this out. So this was, we did this on Friday. Yeah. Render a triangle. Cool. Yeah, so the first goal of today's stream really is to break out hard-coded vertex positions and vertex colors that are currently defined in the vertex shader itself, which is certainly convenient to make sure that we've got the Vulkan pipeline set up. But now that we do know that's set up, I want to move this over into a vertex buffer, and then we can eventually turn the vertex buffer into the result of a quake-3 BSP file. So before we build our command buffers, let's create a vertex buffer. That's a managed resource. I think it's actually just a buffer, isn't it? So, having a brief look at the spec last night, Vulkan has two primary resources, buffers and images. Resources are views of memory with associated formatting and dimensionality. Buffers are essentially unformatted arrays of bytes. Which is kind of what we want, because a vertex buffer is just an array of vertices. Are people still doubtful about the application of Haskell to game dev? Yeah, I think they are, and I, to a degree, share some of their views. It really depends on what kind of game you're making. Like Quake-3, I think we can just about pull off on good hardware if we write this code correctly. The problem is, like any garbage collected language, you have difficulties enforcing like the kind of soft real-time guarantees that you need for a video game. Like you want it to be consistently running at a good frame rate, and it's no good if all of a sudden in like the heat of a battle you suddenly get like a stop the world garbage collection and your game just freezes. And that can be difficult to manage with Haskell. Memory management is especially hard in Haskell because we kind of shouldn't be thinking about it. That said, I think the you definitely can't make a game in Haskell stuff is completely overblown. You could definitely do stuff, and like this Quake-3 stuff I think will prove that you could have a real-time 3D game in Haskell. I don't think we're going to struggle with that bit. A AAA title is something else. So to create buffers, call vk create buffer, and we'll need a device. That's going to be a managed Vulkan resource. Create buffer. That's going to destroy buffer, isn't it? Oh, I should actually just mention that we're live as well. Let me quickly tweet that. Yep. So, we want to create. How do we want to create our buffer? So we need to provide one of these buffer create infos, which needs its S type to be a buffer create info. Pnex must be null. Flags must be a valid combination of buffer create flag bits. We're backed using sparse memory. Specifies the buffer can be partially backed using sparse memory. Just going to zero our flags now. I don't think we need to worry about that type of stuff. Usage must be a valid combination of usage flag bits, and it must not be 0. That's okay, because one of these is vertex buffer bit. What was that? Usage. Size. Size in bytes of the buffer to be created. That's difficult because I don't know how big a single vertex is at the moment. So sharing mode, Q family index count, what's that for? List of Q families that will access this buffer. That's interesting. Ignored if sharing mode is not sharing mode concurrent. Let's go with exclusive, which is the default, but I'll put it in there anyway. Sharing mode exclusive. So we can just use 0 here, which is kind of what we're doing. Null that. Device. Yeah, cool. So size is going to be the size in bytes of the vertex buffer itself. Before we worry about that, like what can I do once I've got one of these buffers? So we are going to need a buffer view because that's what's going to let our shader access the buffer. I guess it's the pipeline that needs to access that, not really the shader. So I did see them mention a vk command bind vertex buffer. Aha, this looks interesting. Vertex shaders can define input variables which receive vertex attribute data transferred from one or more vk buffers. Vertex shader input variables are bound to buffers via an indirect binding where the vertex shader associates a vertex input attribute number with each variable. Vertex input attributes are associated to vertex index bindings on a per parameter basis, and vertex input bindings are associated with buffers on a per draw basis via, okay, that makes sense. we're in chapter 20. Oh, an example. That sounds good. To create a graphics pipeline that uses the following vertex description, the application could use the following set of structures. I'm not so bothered about the bindings and stuff. That's the same as OpenGL. That's not really what I'm looking for. Dang. Just trying to get my bearings in the specifications where these things are kind of used and stuff. So 20.2 vertex input description, application specify vertex input attribute. The graphics pipeline create info vertex input state points to a structure, which is the vertex input state create info thing. Each vertex input binding specified. Yeah. To bind vertex buffers to a command buffer, yeah. So we're going to bind the vertex buffer right before we use it in the command buffer, which will be the draw call. Still doesn't tell me. Ah, this looks good. So copy data between buffer object, not quite. Yeah, so I think it's going to be in this buffer stuff. How do we write to one of these? This is all about images. I'm not too interested in that. To attach memory to a buffer object called bind buffer memory. Possibly. Alright, let's switch back over to the tutorial. I think I've got a rough idea of what's going on in the specification. Now I want to jump over to the tutorial and see if any of that is, my hunch was actually correct there. So, not going to worry about the input description, I'm focusing on the buffer for now. So buffers in Vulkan are regions of memory used for storing arbitrary data. We know that. Then you do exclusive, and then you do create, and you get a buffer. Great. The buffer is being created, but it doesn't actually have any memory assigned to it yet. The first step of allocating memory for the buffer is to query its memory requirements. I'm going to do all of this in here. So that needs a device, a buffer, and it's going to stick stuff into VK memory requirements. We've got that with this alloc and peak function that we wrote yesterday, no, Friday. Get buffer memory requirements. That, oh, I could probably put that on one line. Device, buffer. So what does that give us? So I guess we have to go ahead and like allocate this memory or something. It's telling us we need size bytes and some alignment. Interesting. We're going to have to find the right type of memory to allocate, which I do with get physical device memory properties. Is that maybe up in... device memory in chapter 10, memory allocation. Maybe have a look at this actually. Host memory is memory needed by the Vulkan implementation for non-device physical storage. That I don't think we're worried about. Memory properties of a physical device describe the memory heaps and memory types available. To query memory properties, call this, which we're going to get back a memory properties structure. So I also need a physical device passed in here. It's a physical device. I did not hear that John Carmack had announced he's making an indie FPS. Have you got a link to that news? That sounds interesting. I know he's always been interested in functional stuff. Same with Tim Sweeney. Okay, so now we've got a memory properties structure. That tells me, maybe let's have a look and see what's in this structure. So memory, in fact I might be able to show it. Physical device and device. Destroying the device, destroying the buffer needs to know the device. And we haven't actually finished that. Lift that IO into our more general monad. Why are you thinking that we're in the IO monad? Yes, these have to... Did allocate not do the lifting for us? Ah, okay. Let's just take a look at it here. Cool. Apparently do have a show instance, so I think we might just get a pointer, which isn't too interesting. Okay, now we've got loads of interesting stuff here. Zoom into this. You've got one memory type available in my graphics card. Yeah, not worried about that validation error right now. And that in turn has a list of memory types. I might use to remember what this library is. There's a nicer way to format that information that you can kind of get for free with Haskell. Which one is it? Yeah, pretty show would do the job. And we've got pprint. Text.show.pretty. Let's add that as a dependency. Basically, this is just going to give us the same data we had before, but actually like indented and things like that. So this is a bit hard to scan at the moment. No, that's odd. Pretty simple. Ah, it was pretty show. Oh well, let's use pretty simple. So they're like two libraries that do basically the same thing. Let's pprint again. But it comes from text. Pretty simple. Let's spit that up. So, one memory type, and inside this memory type we seem to have a list of things, all of which basically exactly the same. We've got one memory heap, cool. Let's add in, so I guess basically, I think this is a problem of we have to match up what the requirements are against what our physical device could do. So memory type bit 1. Memory type bits. Okay. Carry on with the tutorial. So the AND, some of the physical device memory properties, property flags against the properties. This was we're defining a function here, aren't we? Yeah. Against some memory property flags. What do they call that function? Ah, there we are. So memory type bits, and we're looking for something that has host visible. Yeah, they can do host visible, and they can do that host coherent bit. Very interesting. So yeah, we don't get to see what 15 is. That's okay. So memory properties is, let's go over all the memory types in this physical device memory properties. So Vulkan get field, I think it is. This is going to be, like, what do I need here? Like an index, I guess, or something? They go for every single memory type and just return. Okay, so just trying to find a memory type. That's actually going to be quite simple because there's only one. But let's do this probably anyway. Memory type index. So what I'm going to do is take this list and zip that against all possible indices, and that's going to give me I and a memory type, and I only want memory type indices that match a particular guard. So memory type bits. This seems okay. What is this memory type bit saying? Memory type bits is a bit mask and contains one bit set for every supported memory type for the resource. Bit I is set if and only if the memory type I in physical memory is supported for the resource. There, so I need that I to be set, okay. So we got in our requirements memory type bit's 1, so that'll be index 0. We'll do test bit. Memory type bits from the requirements against index I Memory types is an array field. Yeah. How do I turn that into a list then? Yeah, cheers for joining. The problem is basically this get field function expects to get something that's not an array, and we are trying to use it with an array. So this can read field, can write field, can read field array, but that requires indices. Okay, this is a bit annoying. So I is actually going to be 0 up to memory type count. Memory properties. Memory type then. Is get field array, and that takes the field name and its index. Oh, man, this, I don't have it at the type level. That's not going to work. There's got to be a better way of doing this. Okay, I'm going to have to do some type level magic just to get into this. So in typelets we have with, no? Guess we can do some net val. I really don't know how to do this actually. Nothing really takes a pointer. Let's have a look at this data structure and see what instances it has. Okay, so if it has field, it doesn't really give me anything interesting. Okay. The only option to get into this is 0 at the type level. Okay, so we have to construct SumNat. Which gives me Run that proxy. I don't think I can get access to the types there, so get field array proxy. I think that should work. That's the right type anyway. To access those types, I'm going to need scoped type variables. I think they have allow ambiguous types turned on for this to work. What's the definition of can read field array? Okay, so I think I need polychimes on. Better. That can actually go here. It's too polymorphic now. Don't really need polykines anymore. Incoherence into the 2, please not. Choice depends on the instantiation of F name IA. Actually, it does seem suspicious that I haven't had to even supply the type class here, so what if we do that? So I do want has field F name A, is field a rip. How do I get this Vulcan in bound thing then? How does it know how big it is? It's like it's not statically defined. Not entirely seeing this. I have no idea how to provide that proof. I've just got an example using this. Nothing too interesting. Oh, okay, so it just has to be within max memory types. But still, how do you prove one of those? Okay, it looks like, yeah, this is looking good. So, what was it again? So it's got to be strictly less than, so we need to get one of these. If I can witness that, then we're good. So I've got a proxy, and now I need to compare that proxy against whatever that max bound was, which it's going to be. This is really annoying. That then gives me, if I get one of these, I get a proof, and I can unwrap that proof, REFL. I really hope it's happy with that. So you need data type, no, GHC type, let's compare, which comes out of typelets witnesses. So let's have that. So basically what this library is doing is enforcing that indexing into an array is proved to be within some bounds. So basically that it's between 0 and the maximum possible index, which I feel is, like, this is obviously correct, but it doesn't give us a huge guarantee anyway. All we're saying is that this I is within VK max memory types, which has nothing to do with the memory type count that we were given. So it's still possible to crash this runtime, so I'm not really sure if this is really worth it. So we're going to unpack equality, data type equality. I don't have proxy in the scope. Maybe if Haskell had better facilities for working with like dependently type programming, which is basically what we're doing here, this wouldn't be quite as painful, but I'm having to jump through a lot of hoops here. You expected a list of B0. Why? Oh, and that's still unhappy as well, because these overlapping instances. So I guess we're going to have to specialize this to, what is it, physical. Keep that general. Still not happy. This is crazy. Is it really this hard? We did this in Get Physical Device Properties. So another option is we could just like manually read that data ourselves, which I think is probably going to be a better option. Actually need to alloc array, do I? So I know how many memory type peak array memory type. Gonna have to cast that. And then the pointer is going to be Vulkan unsafe pointer on the memory properties to get to the start of the structure. And then I'm going to offset that pointer with the field offset into the field that I'm trying to read, which was what, memory types? So I have field offset. about that? Now I can go back to zipping. Still doesn't know what that is. I wonder how they... Actually, I just realised, like, the show instance is able to pull this data out. So how are they doing that? And why does the show instance suggest this is like an array of arrays, which it isn't? Ah, okay, so yeah, they're literally doing like some pointer arithmetic or something to get to this. I don't know what the hell they're doing here. That's really questionable, actually. Yeah, so they don't even take advantage of the fact that they've got this memory type count. Just actually enumerates through every possible memory location up to max memory types, which is definitely wrong. So when we had that print instance earlier on, I can find that still. So we saw loads here that are all identical, and that's actually because we're reading zero memory. We shouldn't be seeing any of these at all. There's only one memory type count, so we should have only seen one entry in this array, which also shouldn't be an array of arrays. So I've got a bug report data file when we're done. Not the end of the world. Hey Red. Okay. So now I think we've got our memory type. Go back to using the tutorial to see what we need to do with that memory type. So we're doing this type filter. The other one we have to do is this. Is the memory type's property flag, can I AND it? Yeah. With the properties that we require. So memory type, get field property flags. I'm going to AND that with the properties that we require. Oh no, sorry, I'm just going to do with that, which is we are looking at a VK memory type. Oh my god, this is insane. Yeah, VK physical memory requirements. It's called device memory properties. Physical device memory. Yeah, okay, so this guy can go. That was horrific. I never want to have to do that again. Wow. Might be okay getting rid of that. No, but what if I peak array at that's a bit nicer. Cool. Okay, so this is possible memory type indices. Print that out as well. Oh, I didn't return it. Now that I've got those, find memory type just uses the first one, so I could this should just say 0. Yeah, great. Cool. So memory type index, we're going to pattern match over all the possible ones, and I'm just going to take the first one. If we didn't get anything, no possible memory types. If we did get something, let's just return the very first one. That's our memory type index, which now allows us to allocate some memory. Is there a corresponding deallocate? I guess I need that memory to stay allocated, so let's just allocate it and leave it. That needs a device, the allocate info. No custom allocators, and that gives me back to memory, so let's haven't defined allocate info. Let's type, size, and a memory index. PK set. Let's type. So allocation size. Presumably exactly the same amount of data. And memory type index is memory type index. We needed that size and bytes earlier on. Let's bind it. We are going to come back to that. Do I have to allocate, align that? No. Oh, it's already in my memory requirements. Okay, yep. Needs a bit of binding. Cool. Happy with all of that? We should now have some memory allocated on the device. Oh, then we got a, if the memory allocation, we can now associate the memory with the buffer. Sounds like a good idea. Size is still 0, but that's not the end of the world. So bind buffer memory. Takes a device, a buffer, some device memory, and a device size. Device. Buffer. Memory. I don't know what this device size is. I use 0. Fourth parameter is the offset within the region of memory. Cool. So we bound the allocated memory with the buffer. The next thing you have to do is fill it with some data, which we do by mapping the buffer into CPU memory. Oh, that indentation's a bit subtle. Okay, so how does that look in Haskell? EK line, what was it, map memory? That will give me a pointer. Yeah, okay, cool. So Vulkan. That does throw, that's okay. So we bind it. Actually, I'm going to keep that separate. Yeah. DK map memory. Device memory. Size. DK whole. What was that? Yeah, we'll do size and bytes. Bytes. Memory map flags. Okay, so there aren't any flags that we could possibly use. Once we're done with it, we're going to have to unmap that, which is the device and some device memory. Okay. So let's do a mem copy. In fact, no, rather than that, we can do so we can poke array mem pointer vertices and then that. Cool. The create vertex buffer is going to take a list of vertices for now. This will probably change when we get to loading the BSP actually, because the BSP itself, we can basically read that file directly into GPU memory, which is pretty cool. So v3 is going to come from the linear library and has a nice memory layout, which is just 3 floats back to back, which is exactly what we want. Linear meaning linear algebra. So this create vertex buffer now has to be given the 3 vertices that are hard coded currently into the vertex shader. So we've got vertex at, oh, there'd be 2s. So these vertices are actually device normalized device coordinates. So I'm just going to hack it for now and carry on passing the normalized device coordinates in. So then this guy is minus 0.5 and that's 0.5. Import that constructor. Yeah. So, in order to be able to actually write these vertices to memory, we have to define what their memory layout is. So the size of a vertex is the size of the pos. In fact, we can cheat a little bit here and use generalized new type deriving. For now, we're lucky about this. In fact, this is kind of cool. I've never really thought about doing this. Generalized new type deriving, which is just saying the memory layout of a vertex is exactly the memory layout of a dimension free vector of C floats, 32-bit floats. Okay, so I'm not really expecting anything to change in terms of the runtime behavior, but it'd be good to see, we've still got some validation errors. So the problem we've got is I said the size of bytes is 0, and that's not true. Error out of device memory is a little worrying. So this is going to be I'm just going to quickly run some buffering. Choose that message. I will just be back in a couple of minutes. Okay, so I had that running while I was quickly out of the room, and the good news is, yes, once we specify a non-zero size, then we don't get the out of memory error. This triangle is still coming from the vertex shader, however. So our next job is to bind the vertex buffer into the shader. So yeah, we've done all of that, and yeah, bind the vertex buffer. I'm going to leave that out for now. Let's go. We've got to specify this vertex input description, which is something that gets added to the pipeline, the graphics pipeline. Let's have a look, see if we can find this in the specification. It's going to be this vertex input state. So, attribute descriptions. There's a pointer to an array of vertex input binding description structures, so we definitely need some of those. And we'll probably need some attribute descriptions as well. It's just going to be the one. So let's start with the vertex binding descriptions. So we now need to get a vertex binding description. So what do they look like? Vertex input binding description. Vertex input binding description. Great. So binding is going to be binding 0. The stride is going to be the size of a vertex. And the input rate not sure about that one actually. Ah, okay. Per vertex, I think. Good. And then we need to do some attribute descriptions as well. It's right here. So we'll set location 0 to correspond to binding 0. That contains a format, and its offset is 0. So what are formats? not really like an RGB format. No, a bit confusing. The formats are specified using the same enumeration as colour formats. Yeah. So vec3, yeah. So we're saying that our format is a vector of 3 components that are each 32 bits, and it contains S floats. I don't know what S float is. You can look that up in the specification. Free component, 96-bit signed floating point. Yeah. That sounds perfectly reasonable for vertex positions. So, the pipeline setup. Got our attribute description. We've got our input binding description. We just need to change this to not have positions going from there, but to have in vec3 layout location 0 is in vec3 a position. Yeah, we'll just take the XY coordinates out of GL position. Good, so that's recompiled. Now if we new run, we should see nothing because we haven't actually set up the bindings. Just the validation layer will tell us about that. In particular, the things that we're missing. Yeah, so something popped up and then immediately went away. We've got a segfault. Pipeline state object expects that this command buffer's vertex binding index 0 should be set via command bind vertex buffers. Yeah, we never did that, did we? Okay, let's do that down here. That's about, I guess we have to do that every time we build our command buffers. Take our command buffer, first binding, one binding, count, we actually only have one buffer so I can just say unsafe pointer vertex buffer, and the offsets. So, okay, what about that? Bingo! So now, if we got this right, our vertices are now defined in the source code itself rather than in the shader. Perfect. Cool. So I suppose the only last thing to do is get these vertex colours out of here as well. So let's bring those out. So 1, 0, 0, 0, 1, 0, 0, 0, 1. Need to add that into here though now. Let's say foreign C. Okay, so I'm going to try and hack this a little bit. So the GHC forthcoming extension deriving via would really tidy this up. But basically what I'm saying is a vertex is itself a two-dimensional vector where the first component contained... that doesn't really make sense, does it? We could... A vertex is a two-dimensional vector where each component is itself a three-dimensional vector of components. That'll work well enough for now. We're going to have to revisit that because not everything's going to be the same size in the future, but... I don't actually need that at all. There was a type alias. So now we just need to change the vertex attribute description, I think. So position, attribute count, and color. Attribute description, sorry. Oops. Colors are the same, but their offset is simply the size of the position component, which was Seems to suggest we're not using this, but we are. Ah, doesn't know what size of is. Good. So that sets up the pipeline. We need to change this to oh, I need to recompile that. Do we have to change? These bindings? Probably not. No, maybe that's okay. Yeah. Vertex shader can use it at location 1, but it's not provided. So create our vertex buffer, and this is all the noise about getting some data in there. Or did we miss out? Ah, we didn't change the location. We said that's location 0, so it's location 1. That's why our triangle changed shape, because our colour attributes ended up overriding it. Bingo! So just to double check that, let's have a all red triangle. So setting the red component to 1 on all of those, and if we run that, we shouldn't need to recompile our shaders, obviously, because now they don't have any data in them. Sweet. Just a couple of warnings to fix up, and then I think I'm going to wrap this stream up there. So this guy throw. Don't need that tightness witness nonsense anymore. We can get rid of that. Take it out for now. We may come back and re-add that. Take that. 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 Good. So I don't have a dependency on either of those. What's wrong with the draw call? So the draw call at the moment is right, I think, right? So yeah, number of vertices to draw. We're not drawing any instances, so I think that's. I don't think there's anything wrong with that. Oh, I see what you're saying. Yeah, that's a fair point. So yeah, the question now was, can I change this to be a little bit more correct? And obviously, it's the right number, but that just happens to coincide with the length of this list. So. For now, let's just move this out. Like the structure of this is all going to change when we start getting into loading BSP files, which we're getting quite close to looking at. But for now, let's just do it that way. There. Can I actually read that info from the Vertex buffer though? Or hopefully you're happy with the list that I've used. Oh, interesting. So I didn't know that. Oh wait, that command buffers, he defines this, doesn't he? That's, what am I talking about? No, it's exactly as I expected, yeah. So given the command buffer, set it to the length of the vertices. So there's nothing magic that reads the length of the vertices out of the vertex buffer. Or at least we're being consistent and not duplicating information. Cool. So yeah, so I'm going to wrap that one up here. I think that's pretty successful. Got to kind of where I wanted to get to there. So we've, just to recap, we have fixed a tiny little bug where we weren't using the Vulkan loader entirely correctly. So that's just a little bit of correctness there. So the binary we produce is now dynamically linked against the Vulkan loader. And then the main thing that we've done today is introduced a vertex buffer object, so that we're able to actually send vertices directly from our code into the GPU rather than hard coding the location of all those vertices in the shaders themselves. I think in the next stream, the next logical step is to change the definition of these vertices from being device coordinates, that is, they're basically two-dimensional coordinates onto the screen, to be proper three-dimensional coordinates, and we will use a projection matrix to turn those back into device coordinates. And maybe we'll also introduce a V matrix just to start to get some sense of three dimensions. So that's going to take us through working out how to send other information into the shaders. So we're going to have to send some matrices into the shaders rather than just pull stuff out of buffer objects. Yeah, so that will probably be on Tuesday or Wednesday. So if you're interested, just follow me on Twitch, or I'm Charles. No, I'm not. That's my Twitch account. Sorry. I'm Acid2 on Twitter, which I'll also be tweeting, going live announcements there. Anyway, cheers guys. See you on the next one.